2018 Perspectives on Digital Pedagogy, Lunch and Learn. We have with us today distinguished visiting professor Bob Panoff, Wofford class of 05. The series began last spring with primarily humanities-focused talks, and so we're really excited to broaden the spectrum, because the idea behind these talks is various perspectives. And so we're excited to have Dr. Panoff talk to us about computational thinking for everyone. Please give him a hand.
So part of the understanding of the group is to talk about what I'm going to address today. I thought about with the digital pedagogy group, and I said, well, what is digital pedagogy? Ped refers to foot. Agog means that you're impressed by. So people that are impressed by large digits and feet. Perhaps. I don't do politics. Politics, again, can be thought of as coming from two roots. Poly, that means many, and ticks, which are blood-sucking parasites. But when we talk about computational thinking, it is such a huge umbrella that I want to make sure that everybody sort of can fit their view of it under it. The noun is thinking. Okay? Computational is an adjective. The noun is thinking. Without the thinking, no point in doing it computational. If you say, oh, well, we're going to use a computer, and that means I don't have to do this. No, you probably have to do more of that. More math, more thinking that goes on there. There's quantitative reasoning that goes on. There are multiple representations. There are using equations as stories. To start off, let me just say that there's a fundamental theorem of presentations of this sort, and that is that satisfaction is reality divided by expectations. So my goal is to lower your expectations. See, you're laughing. When I did this talk at the Department of Education a couple years ago, people didn't laugh until I explained, because if you divide by a smaller number, you get a bigger number. Because for them, it was just an equation. It was just take any two numbers, divide them, and you get another number. But there was no thinking that went into these things. So we'll talk a little bit about what we're doing and how we're doing it as we kind of progress. If you have a device you would like to follow along, some of the talk will be available at this website. So I want to tell you a little bit about me and remind you of, some of you anyway, of my relationship with Wofford. Before we do that, I'd like to ask the question, I'm the founder and director of what's called the Shodor Foundation. I don't want to know the answer. I want to know if you know the answer. Does anyone happen to know where the name Shodor came from? So as part of my mission to change the sound of education from what is the answer to this question to something along the lines, well, how could you figure this out? I'll tell you a true story, and then we'll see if more people at least have a conjecture. When I was a physics professor at Clemson University, and there is no P in Clemson, but when I was down there back in the late 80s, a young man needed me to sign his scholarship form, but he couldn't remember my name, so he couldn't find my office, so he couldn't go to the directory to look me up because he couldn't remember my name. So he goes to the physics office and says, you got to help me. I've got to find my professor by 4 o'clock because I got to get him to sign this form. But I don't remember his name. But what I do remember is that he's short and kind of dorky looking. So if you were asked, where do you think the name Shodor is?
We're looking at it.
How many people think down, without my telling you explicitly, that you could at least figure out what and that's a little bit of what we're doing with computational thinking, is that the thinking part is, how do you know if it's right? What do you expect this to be? What do you observe it? How do you observe its behavior? And have you learned anything? And how do you know if it's right? And so part of that, again, is going to come down to some aspects of quantitative reasoning. That's part of computational thinking. But also when we're using a computer to compute, there are things that are unexpected, especially at the college level, where students have often graduated from a high school where they walked around expecting to use some hand calculator for a lot of stuff, and they weren't even really using it for anything except a crutch. One of the questions comes up then is, what do we expect computationally? How could we do certain types of things? So let me just measure a little bit of the class here of who you are and what you might know. Oh wow, none of the markers have anything on it. I was. If I ask you what 2 plus 2 times 2, what is that? What is the value of that expression? Who would like to conjecture?
6.
You would say it's 6. Why do you say 6?
I'm partially guessing, but don't you multiply before you add?
Right. There's a convention called order of operations, but you don't have to because it's not a theorem. But if you don't, you would get a different answer. 2 plus 2 would be 4 times 2 would be 8. That's order of entry. And what a lot of the students have done is they have become used to calculators doing the thinking for them. And so they end up on a Mac or a PC at the college level, and they pull up a calculator. There's a calculator, and we'll do 2 plus 2 times 2. And you get 8, not 6. You say, well, wait a minute, that's not expected. Now, is that 8 right or wrong? It's not wrong, it's just unconventional. We have a convention to do the math one way, but if we don't follow that, and what often happens is students who are used to having a calculator doing all their thinking for them will go down to a lab or pull up a computer, and on the computer is a simulation of a calculator. So you have a computer which is perfectly capable of compute, but they don't know how to compute. So they pull up a calculator because that's what they're familiar with, and they think that that calculator is going to do what they had already used when they had a calculator. And now they say, I don't need one because I have a tablet, I have a PC. Now, if you actually look for a calculator and you say, show me a calculator, then you get something that says 2 plus 2 times 2. And now you get 6. You say, wait a minute, I pulled up a calculator on a Mac and I got 8. I pulled up a calculator on a Mac and I got 6. Well, it turns out pulling up a calculator on a Mac or a PC is not unique. Right? It's one of the things that can happen. And if you pull up your phone, there are simulations of calculators on your phone, and there are even some that if you hold the phone, let me see if I can actually do this with my post-cataract eye. If you actually had some kind of calculator, and you hold it this way, you get one calculator. If you hold it this way, you get a different calculator. So the answer depends on how I hold my phone. But it could, depending upon, what's happening at some particular part. So we're going to talk a little bit about expectations, and one of the grand expectations all of us have to put up with. Let's see if I can find where I put this. Right here. Is your friend Google? So I type in 2 plus 2 times 2 into Google, and I don't know if you can see it, but Google says, that doesn't look like something Bob wants me to search for. That looks like a calculation. So just in case that's what he wanted, I'm going to do that first. But then I'm also going to find 25 trillion web pages that have more than one 2 on them. So you want to do a search, but it looks like a calculation. Google is assuming I could be helpful because I know what you're thinking. You're thinking you want this to be evaluated. Now, if you had come back 1,000 years ago, the problem might have looked like this. Right. So if you're teaching history or linguists or something, that you can basically figure things out, that there are more than one numeral to represent numbers. Right? The Arabic 2, the Roman 2. Can you think of another numeral for 2 that if you saw it, you would think, that's funny, it doesn't look 2-ish. Right, so if I came over here and said 2 plus 2 times 2, I don't have a 2. I have a YO.
But it figured it out.
Did it figure it out? Oh, yeah. See, it knows what I'm thinking. So the point is that one of the things that faculty have to be prepared for is that students have Google on their little device, their medium device, their big device, and they may think they don't have to think anymore because they can just Google. And there is something to be said about information algebra that Google, and this is part of the power part of the talk, then we'll explain the peril part of the talk, that the power of computational thinking is I have tools that if I use them well, expand my ability to think. But I have to use them well. There's an essay on business management called The Manager and the Moron. We are beginning to realize that computers do not make decisions, they only carry out orders. It is a total moron, and therein lies its strength. It forces us to think, to set the criteria. The stupider the tool, the brighter the master has to be. And this is the dumbest tool we've ever had. All it can say is either 0 or 1, but it can do it awfully fast. It doesn't get tired, it doesn't charge overtime. It extends our capacity more than any tool we've had for a long time because of all the unskilled jobs it can do. By taking over these jobs, it allows us, in fact, it compels us to think through what we're doing. But though it can't make decisions, the computer will, if we use it intelligently, increase the availability of information. I asked Peter Drucker, 1967. I got this out of the discard pile at Clemson. Somebody was throwing it away because it's a great book. He's got all kinds of things talking about, you know, the role of computers and what they're going to do, but nothing's changed, right? At least not in 50 years. This idea is that the thinking part has to be provided by the carbon-based life form, so the silicon-based life form does what it's told. And it will only do what it's told if it's working, you know, at its optimal best. So let me give you an example of the computational thinking and the peril. A lot of news these days about Mars. We just lost another Mars lander. Something happened, somebody didn't do a calculation correctly or something. And I asked the class what they knew. Like, for instance, which planet is bigger? Which has more mass, Earth or Mars? Anybody know? How much? Are we a little bit bigger? Twice as big? 5 times 10, 20, 50?
6.
Huh?
6.
6? Could be. I don't know. You know, or it's just you've heard it somewhere, you're remembering?
I'm remembering that the gravitation is 1/6.
So suppose we wanted to compute something that would give us the answer, like the ratio of the mass of the Earth to the mass of Mars. Now, if that number ends up being bigger than 1, Earth would be bigger. If that number ends up being less than 1, Mars would be bigger. But if I want to calculate the ratio, what do I need first? I need to know how to type. Okay? Because if I type in the words, mass of the Earth divided by mass of Mars, then Google reaches into the deep, dark recesses of the internet and pulls out the mass of the Earth. Finds the mass of Mars somewhere, forms the ratio, and tells you the answer. My question is, what reason do you have to believe that? Because a couple minutes ago, or not even that, you said we need to know the masses to do this ratio. Do we now know the masses? No. But we have something that looks like a ratio. Has no units, good sign. You know, the kilograms canceled. But the question is, what did Google use for this? How do we know? So you might come up and say, well, maybe this would lead you to do a little bit more investigation. So let's look up the mass of Mars. And the mass of Mars is 6, see, it shouts it out because Google knows. This is the font equivalent of, trust me, I know what I'm doing. Don't go below the screen bar because there's just stuff down there that will confuse you. But what we will do is we'll source this. And where did Google get this number?
Wikipedia.
So you go to Wikipedia and you say, what's the mass of Mars? And there it is, 6.39 times 10 to the 23 kilograms. Oh, and it has a little 5, which is a reference, and if you look that up, it's not this number either, nor is it the other number. And so if you start pulling on the string, you say, well, what is the mass of Mars? If you didn't know beforehand, we certainly don't have any way of taking our professional expertise and applying to it, except consistency. Right? So if you actually come down here and look at these numbers, you know, you get 6.4171, 6.416, 6.4169. You know, you could actually go down and click on 10 different links and get 10 different values. It depends on who measured it, how it was measured, and were they trying to be precise, or did they just give you sort of an about number? But it turns out that if you think of 6.39 and it turns out that it's bigger than that, then when you calculate the retro rocket needed to slow your lander down enough to land smoothly, you could be off. And it may be enough that we now have pictures from another satellite showing the crash site of what the Europeans had just sent up there, and it's not really. So the part of this thing is there's stuff out there, but what reason do you have to believe it? As a scientist, I have come to use an adjective for most of what's on the internet. The adjective is indefensible. It might be right, but I have no reason to believe it, except if I already know it, that's great. If I don't know it, Google isn't necessarily going to give me something that's good enough that I can be sure. What I can find is a range. You know, the gestation period for rabbits is between 26 and 35 days. Right? So depending on how you use that in the population model, you might have 11,000 rabbits, you might have 1.5 million rabbits. Well, it's a range. So you can figure these things. But the thinking part of it is something that's there, and as we're going through. So what I attempt to do is to answer the following question: how much information is on the internet? Any guess? IMHO. None. Because what's out there is noise. And if you capture the noise and filter it, you get a signal that you could then decide the pattern of signals that is given to you. We call things that are given to us data from the Latin. And once it's given to us, we have to ask ourselves, just because it's given to us, do we have to take it? You know, what reason do you have to believe it? So using Panoff etymology rules, when a human forms a judgment about what data they're going to allow in to their worldview and what they're going to shun, then you create information. It is the result of a human judgment. It is not the result of a Google search. It is the judgment that comes with the search to ask the question, what reason do you have to believe this? How do I know if this is right? And things, some of you it may not matter as much, but I work in material science, and one of our favorite things to ask is the boiling point of radium. The boiling point of radium is 1,737 degrees C. The boiling point of radium is 1,500 degrees C. The boiling point of radium is, what's the third one?
1413.
1,140 degrees C. See? I mean, the point is, for some things, it's really bad. And do we have any chemists here? There's no standard pressure. There's no indication of what isotope is used. None of these websites give you anything except, oh, you were asking a question that sounded like, what is the answer to this question? This is the answer to this question. Well, if I ask somebody else, I get a different the answer. Now, what the internet is good for, and what some web searches are good for, and part of what I use, the digital and the web part, is to show students there is, in fact, a variety of ways of looking at something. There's more than one way to look at it. One of our typical exercises in the modeling class I'm teaching is I have them look up scientific method, and I want them to look up images for the scientific method. And what you notice is, are all of these ways of visualizing the scientific method the same? How are they the same?
Colorful.
But if you notice, every one of them says the. Not everyone, but many of them say this is the scientific method. It's not one way to think of it, and there are other people who have different opinions. Right. But it's important to see that there are more than one ways of looking at things. There's more than one model. There's more than one approach. And even in science, very rarely is the approach, what is the answer to this question? It's how many different ways can we study this, and what do we learn from looking at it different ways? There are multiple representations, and some of the representations tell us more than others. I don't know if this is going to hurt your brains after so little coffee with lunch. But if I was to come up and ask the question, is 899 prime? Prime? No, I didn't think there was going to be a quiz on it. But a prime is a number that's divisible only by 1 and itself. That's one way to look. How would you test this? Anybody have a suggestion? You could go through, it's not even, so it's not divisible by 2. The digits don't add up to a multiple of 3, so it's not divisible by 3. It's not even, so I can forget all the even multiples. It doesn't end in a 0 or 5. You could do that. Or I could represent it to you as 900 minus 1. And nothing happens, but I could say that's really 30 squared minus 1 squared. Did you hear that, Wazowski? That's the sound of change. Those are the winds of change. Because now I have represented this number as the difference of 2 squares, which I learned somewhere that x squared minus y squared has factors. If it has factors, it's not prime. In fact, I could even figure out what the factors are. 30 plus 1 and 30 minus 1. Because that's how, so if it has factors, it's not prime. So change the question, is it prime? That's one way to look at it. Another way is it doesn't have factors. Because maybe that way of looking at it brings other things to mind, so that when you look at it, you say, wait, I think I could do that. And then anchoring, there's certain knowledge, it's not Googleable. You've got to know certain things. Like for instance, if I was to ask you, and a quick hand up if you know it, I want to see how many hands go up, how fast. What is 4/9 as a decimal? I see 2 hands. Okay.
What's a decimal?
Now suppose I ask, what is 1/3 as a decimal? Who knows how to represent a third? What is it? Right. Now what if I took 1/3 of a third? What is 1/3 of a third? 1/9. So if I take every one of those 3's and divide it by 3, what do I get? Now what if I multiply that by 4? What do I get? So what is 4/9 as a decimal? So I can start with something I know and cannot unknow. I don't know when I learned it, but at some point, 1/3 became 0.333 forever. And I know that. I don't even know how I know it. I don't think I divided 3 into 1 just now and did it over and over. I think I just pulled it up and there it was on the screen. But I can take that and say, now how can I use that as an anchor to think about what I'm going to compute? So what I really want is 4/9, but I don't know anything. Yes, I do. 9ths and 1/3 are related. Oh. And you back up and in a couple of steps, you can recover them. So some people would call that quantitative reasoning. I include that in the computational thinking part of what's going on. So in terms of what we're doing, at least my role with Wofford has been to explore for many years now the complementarity of computational science education, which is using computer models and simulations and tools to study the content of chemistry, biology, physics, economics, psychology, whatever. And computational science education, which is teaching people how to build a model and how do you know if it's right and how do you test it, and thinking about round-off and truncation and all the things that computer scientists think about for the accuracy and the believability of a particular model. And all of this is based on the fundamental equation of science, which is the right answer is the wrong answer plus correction. Okay? And most of your life is spent dealing with the wrong answer and getting used to it. But it may be an answer that's good enough if the corrections are small. Or you can make a series of successive approximations that make some corrections, and then you get better, then you say, well, maybe that's good enough. Well, maybe I need some more corrections. And the computational thinking comes in to say, well, I don't know the right answer, so I have to evaluate the wrong answer in terms of, well, what does it look like? Is it consistent? Does it do? How wrong might it be? If I were able to calculate the corrections, did it make it get bigger or smaller? Right, so those are all things that we're kind of playing with as we're coming through. Now, in terms of the computational thinking, the idea of what is authentic science, and everybody has their own definition. And I've tried to simplify it for my students as basically coming down to what do you expect, what can you observe, and how sure are you that you're right? And one of the things that's clear is that expectations can change observations. And depending on what you're expecting, we know in physics that if you tell kids to verify the pendulum has a period of 2, they will, even if it has a period of 1.9. Right? Because somehow, psychologically, they know it's 2, they got to get 2, and when they do the timing, they round the numbers up, even subconsciously, and if you ask them what is the period of this pendulum, that's a very different approach. So expectations can change observations. Satisfaction is reality divided by expectations. Right? Your reality, what you observe, things can be very different. Part of the problem is that humans are not very good observers, and so we typically use microscopes, telescopes humanly for certain types of observations. And a number of years ago, somebody said that the computer is the new microscope, it is the new telescope. Right? Because we could use that for many things that the physical device we could do if we had access to it. But computer models are ways of studying things that are also too big, too small, too dangerous. You know, what if you wanted to learn how do small cracks in airplane wings become big cracks? Take 100 airplanes and randomly, you know, in a double-blind situation, put small cracks in some of the wings. Don't tell the pilots, because then they might fly the plane differently. And then you, under certain circumstances, with weather, without weather, turbulence, non-turbulence, measure every couple of weeks as the crack got larger. And there are people who believe that wet lab, you know, actual experimental variation is the only way to do science. And there's a lot that can be done with computational approaches, but you have to think about what's the relationship between the computation and what the real piece would be. And that's hard, because people aren't really used to thinking like that. But expectations can change observations. Observations themselves are hard. We're not really wired for things. But if I put this object in one hand, what do I have in the other hand? And then based on the amount of coffee I've had, then the question is,
Wow.
now when I did this for the kids, they said, oh, I know you do it. It goes down your sleeve. So, no, it's physics. There's an R and there's an F, and R cross F gives me an angular momentum. There's a torque. And it actually gets thrown. Rate times time is distance. The distance isn't very big. The rate is very high. The time must be very small. Right? But the ability to observe that depends upon photons hitting metal, hitting the retina, sending an image to the brain forms an image, it does it again, and then the brain says, oh, that image is moved. But that's not usually, we don't have enough time to form those images. And there's all sorts of scientific things for deja vu, being that when I send something before the other, and by the time the second eye saw it, the first eye already had a memory, and so you say, yeah, I've seen this before. Yeah, just now. But this idea of expectation, observation, reflection is something that, I don't want to scare you, but there's a lot of things in computation where things don't behave as they were expected. Right? So if I do a very simple but dull example, suppose I had 3/6 Oh, it thinks it's, again, I didn't expect to think that it would think that 3/6 was a date. So now I have to come over here and tell it that these things are actually numbers. And I'll give it a bunch of decimal places. Okay, now 3/6 is that, right? What is 1/6? Well, you may not realize it, but Google just lied to you. Because what it really is 0.666 forever, but it can't. So it stops at some point, and then what does it look like it did? So do I have a number bigger than a sixth or less than a sixth? Bigger. So if I came over here and I said, suppose I took 3/6 and subtracted 1/6 3 times. What I'm really doing, as you can tell, is I just subtracted 1/2, which is 3/6. And then I subtracted almost a sixth minus almost a sixth minus almost a sixth. And what would you expect to get? And it says 0, but that's a lie. And the reason I know it's a lie is that if I actually change both of these, actually change both columns to a general math number, then as soon as I put it in parentheses, which is Microsoft's way of saying, don't lie to me. Because if I take the parentheses away, Microsoft goes into Jack Nicholson mode and says, you can't handle the truth. So even though you can see that I shouldn't get 0, you do. Unless you tell it, don't lie to me. And that's unexpected for most things. Now, can anyone suggest another unexpected result? Is the answer positive or negative?
Negative.
Now what I did was I took, according to what it says on line 1, I took exactly a half, that's a power of 2, and subtracted more than a sixth, minus more than a sixth, minus more than a sixth. What should I get? A negative number, and I don't. Because again, Microsoft wants you to feel better, and it knows that you know rounding, but what it's really doing is truncate. At some point it stops, which means what it's really storing in memory is less than a sixth. But when it prints it out as a decimal digital base 10 number, it shows you rounding because that's what it thinks you expect it to show. Now, if you're not expecting that and you're doing calculations that are sensitive, you could get weird things. And students do get bothered by things that are weird and wrong at different times. So this expectation, observation, reflection, and then it's also part of the reflection, getting kids to think about why did you do something and what did you learn from that? I may have told some of you the story of it's a recovered memory from one of my surgeries. I was a little kid, probably 3 or 4, about ready to cross the street because I grew up in America. I did what American parents tell their children to do, which is what?
Look both ways.
So I look one way, I look the other, I step into the street, my mother jerks me back and says, Robbie, what are you doing? I said, didn't I tell you to look both ways? I did. Didn't you see that car coming? Yeah. You said, look both ways before you cross the street. I did. And having done that, I'm still getting yelled at. How is this possible? Because we don't say, look both ways, and if then else, because we don't teach if then else till CS, right? You know, that's why we need to have computer science for everybody, so they learn if then else. Okay, and if the car is coming, then make an estimation of the approaching rather than the car. What I think I was thinking, and this is a very recovered memory, is that it was like when my father took pictures back in the days when only the father had a camera, not every single person on the planet. And he would always say, if you can see the camera can see you. Because that's the lens-to-lens image that you can tell. So I was thinking, if I can see the car can see me. And what car's going to hit a little kid if it sees him? But who's responsible to make sure that the car sees you? You are. And how do you do that? Look both ways. Look, I'm only 3.5. At least in this memory. But the point is that a lot of times we have kids do a calculation, run a model, do an experiment, translate something, whatever it is, and at any stage they say, well, what reason do you have to believe that? How do you know if it's right? Sometimes people parrot things to us because they think we see things, and it might not be. You might have seen this class, we were talking to Lee about these classic math errors that come up to things. But in reducing fractions, the same thing is, suppose I had the fraction 16 over 64, and I wanted to express that in lowest terms. Without straining too hard, does anybody? 1/4. And how did you get it? And Billy says, I canceled the sixes. Well, that's what I saw you doing. You had a number, a line, and a number, and then you crossed off something above the line, and you crossed off something below the line, and you said that was the answer. He said, yeah, but I was crossing out factors, not digits. Yeah, but that's not what it looks like. And by the way, that's the right answer. So how come I don't get credit for that? And there's a big difference between what we call solving the problem right and solving the right problem. So solving the problem right depends on whether you're a physicist or a computer scientist. Sometimes we call that verification. Validation is you solve the right problem. And then for education, we talk about accreditation. Is this problem the right one for me to teach the concept I'm trying to get across to my students? And again, it depends upon what the method is, but you know, as we're trying to do these things, we're kind of getting into, you know, a whole range of science and scientific inquiry. I'm going to skip over this for a second. Now, from a computational standpoint, as a thought amplifier, one of the changes in what we can do with numbers, especially with data, is that we can use computational tools to help us handle much more data to see what the patterns are in the data. Oftentimes, we use such little data, we don't really see a good pattern in that particular data. You know, let me show you an example of a scatter plot. Okay, so this is at Purdue Calumet. By the way, if you go out in the hall, you guys got great scatter plots too. Try to convince the security guard that all you're doing is taking pictures for a math class. But do you see any difference between the tens of thousands of entries to this door compared to the tens and thousands of entries to this door? Any given whack of a hand or a shoulder or a purse or something on that door may not make a difference. But what might be some observations that are consistent with the many, 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 many data points that are all summarized in a single scatter plot?
Women hit below the pad. Some of the women
What
hit
women?
below the metal.
How do you know they're women?
That they read the sign. They self-identify as women going in there.
But in terms of the sheet that's black on at least one side, it appears that whoever's going in that door compared to whoever's going in this door. Now, what might be other explanations for that besides men and women?
The door on the right's taller.
Well, the photographs are supposed to be scaled. I'll try to do a better job. They're actually the same size.
Paint's thinner. On the door on the right.
Could be, so it's been warned more. This one opens this way, this one opens that way. So people are hitting one with the left hand, one's hitting the other with the right hand, and maybe the left hand doesn't go up as high as the right hand. Could be.
Maybe people that use the right door have cream or lotion on their hands.
They might. But the point is that there are ways that you can actually see that in terms of even binding, that there's a wide variance here and there's a smaller variance there. You see no hitting down here, you see a fair amount of hitting down there. But by looking at all the data at one time, but that's a lot of data. And this particular data took 15 years to generate. If you had to watch that data as it was being generated, that's not nearly as interesting a lesson learned as once you have the data, show it to me in a form, some kind of visualization. It might be a graph, it might be a plot, it might be color involved somehow that shows you how these things are done. But that's a physical example of a scatter plot. Now, other things that we've tried to do is create and extend tools that, by the way, are free. They run on anything, and at least our tools do. Not everything does, and that is a problem at Wofford. There are kids that have tablets with a keyboard, and they think that's a PC. And there's software that runs on a PC or a Mac that will not run on a tablet. And it's, you know, it's not bring your own device. Not if the device doesn't run the software you need them to run, teaching the class you're teaching for the lesson you need them to learn. You say, well, that's not fair. Well, yeah, but that's the real world. There are certain pieces of software that don't run on tablets. Anything written in Java won't run on tablets. For this particular case, we wanted to demonstrate variability because the generation of the visualization shouldn't be an inhibitor from using that if it's a powerful way to look at data. This is a histogram. Has anyone tried to use Excel to make a histogram? How many steps? What's the first step?
You can find me where it is.
Okay, and then when you find out that it isn't, then you got to get the sysadmin to install the rest of Excel.
The add-on.
Yeah, I mean, it's just...
Do the rest of it. Yeah.
But one of the things that we wanted to do was to spend more time thinking about how do you know if it's right, and is that the right histogram for that data? Or is there other ways of looking at the same data? So this happens to be 173 math SAT scores from a high school in North Carolina, and surprise, surprise, the average of all those scores is about 500. I'm here to tell you the average of every high school in the United States is about 500. Because 500 is halfway between 200 and 800, and all the children are average. It might be 480 to 520. It turns out that's 500. And when they announce points are changing, they're changing by 1 or 2 points, but they don't tell you as the scores are renormalized every year. Right? So one year's can't be compared to another year anyway. That's beside the point. A lot of people don't want to use this because they say it doesn't tell you anything about the students. There it is, center peak, even tail, continuous. It's just a blob in the middle. Some do better, some do worse, but the SAT doesn't really tell you very much about students. Right? If you say, well, if you looked at it a different way, there's a bigger chunk. Sure enough, everybody's in the middle, about 450. It goes down to above 300, up to 650. You get a high tail there, but it doesn't really help you very much. But if I had to make a different histogram every time and rebin the data every time and make this over and over and over, as opposed to just saying, let me take the width of the interval and move it. And while I'm doing that, I'm going to watch what happens to the data. And what I see is that at 450, 550, 650, and 750, I get local maximum. In fact, kids who know arithmetic, kids who can solve one equation and one unknown, kids that can solve 2 equations and 2 unknowns, and kids that can work for 3 hours on a Saturday morning without getting tired and putting their head down and giving up are not the same kids. It's actually overlapping distributions. No, that's not right at all, because I made a histogram, right? And it's center peak, even tail, continuous. I said, yeah, but I made a histogram too, and I can see something in the data you can't see, and I never would have seen that if I didn't have the ability of easily looking at a wide range of representations, not just one histogram. Not with, oh, a histogram has 10 intervals. How do you know? How do you know that's the right number to look at the data? What's the data tell you? Not what does your way of making a histogram tell you? And that type of variation that changes the question from what is the histogram to which histogram and how do you know, and are there more than one way to look at this data? You know, if you use smaller bumps, then look, guess what popped out? A bump right about 350, right? Even lower, there's some kids that know some arithmetic, but just not the main stuff. Fractions, decimals, percents, and ratios, reading and interpreting graphs. That's what you need. So this is one of the ways that computation is assisting thinking. You think about how would I do it differently? Could I represent it differently? But the repetitious, tedious work to do it over and over and over yourself is replaced by your little silicon helper. If you know how to use it, and by the way, all this stuff is from Schroeder is all free and works for anything. We actually have people at Fermilab that use this for some of the analysis. They've modified and got rid of the pretty colors because they didn't think that looked very professional. Right. But that's one kind of an example. Another example is something we did to kill off what I call the big lie. Suppose you had a function that kind of looked like this, but you didn't really know what that function was. Some of us might know that as sine or cosine or something. But if you had a field guide to birds, and you don't know what the bird is, you could look up its features. What if you had a field guide to functions? See anything up there that kind of looks like that? And then you could pick one of those, and now that becomes the function, and every one of your parameters is given a color and something that looks like this. Now, if this was a moving smartboard, I could do it right at the board. But one of the things that you can see is different from the textbook. So if you saw this in a textbook on page 47, you see the graph, you see the equation, and then the lie. As you can see from the graph, if you vary this will change. I don't see that from the graph. But if I change the purpleness, not a purple, but a purple. If I change, Ace Hardware paint. If I change the purple, can you see that the purpleness changes something about the size of the bumps? The multiplier of the function seems to be a scaling event. If I take the coefficient, the multiplier of the argument, that appears to be a squeezing scaling event in the x direction. If I take something and add or subtract it, when I move to the right, it moves to the right. When I move to the left, it moves to the left. But Dr. Panoff, how come you subtract it? Why not add it? Well, because if I add it, it would move the other way, and that's not what it looks like. So you can think about it easier if you write it in a way that lends itself. Now, if I add or subtract something to the whole function, it's a shifting event up and down. And that I can see from the graph. And we can take any function from any book on page 42 and turn it into something where every constant becomes a parameter. I mean, I learned this when I was at Notre Dame. We were taught that constants aren't and variables don't. Constants aren't constants, they're parameters you're going to change. And variables don't vary. It's x, get used to it. Now that's not entirely true because in this particular case, we can change, it doesn't have to be f of x, it doesn't have to be f, and it doesn't have to be x. But it has to be consistent. You can tell what it is that you're doing yourself. And then we could do this with data as well. Let's see if I have. So here's some data. This came from the study of a fire. And the idea was, what is the density, what is the probability of the fire spreading, that if one tree is on fire, if it can't spread, it doesn't. If it has to spread, it burns everybody. And everything in between is not a straight line. It actually turns out to be rather interesting. The question is, what does something like this look like? Right? You say, oh, well, I was in nuclear physics. I know something that I could use for this. I could use, let's approximate this as 99 times the exponential of minus, it looks like it starts going up at about 0.5, and then I'm going to raise that to some power. And I'm going to let the exponent be actually one of the variables. You say, well, how do you know that? Well, I have experience, but if I take the exponential of something that's very, very small, I get 1. And if I take the exponential of minus something that's very, very big, I get essentially 0. Right? So I start at 0 and I end up at 1. Then I multiply it by the height of the step. We teach this kind of thinking in the modeling class because you need to know what things look like. Right? So if I set that, one of the things that you might see is that if I change the exponent at the very high data, I could actually make that data look pretty good. Or I'd have to make it look pretty small to represent the low data. So one of the things that we can do computationally is help people see squarely bracket signs. You've seen these things where it says the temperature is squarely bracket this expression for x greater than this, and something completely different for x less than that. There's not one theory for everything? No. But you can see that sometimes you get better. Now what do we mean by seeing? What if I took the data point and took what I think is the model, and I drop a line from the data to the model, and I use that as the side of a physical square, where I take the error and I use that as the length of a square. What's the area of that square? It's the error squared. And watch what happens at the top of the graph as I get closer and closer to a reasonable. You see the squares are getting smaller? And I can go too far and then they get bigger again. But at some point, the squares are as small as they can be for that thing. What's one word that has the same meaning as small as they can be? Minimum. Starts with L, rhymes with east. So what kind of a fit is this? Least squares. It's a least squares fit. And we make the squares the least they can be, and you can see the error. And now you couldn't do that if you're trying to draw it on a marker board and do it by hand and try to come up with something. But if the whole thing is dynamic, and you set it up once and you get it coded right, and then you don't have to code it because I've already got it. You have a tool. Put in data, put in the function, either choose to have squares or not have squares, move the things around. Now do you notice that when it's good at the top, it's not so good at the bottom? And then you could sort of figure out at the bottom, it's much better, but not so good at the top. But there are tools like this, and we've come up with a number of them. Schroeder is known for these kinds of tools, and they're out there and available to be used to give you lots of ways of looking at data. And it's an opportunity that if you're in a class that has a quantitative component like economics or some things in history or government, you say, well, here's an expression for the change in the gross national product as a function of this, this, and this. You could take that, put it in here, and then say, now, let's do an experiment. What if this was bigger? What if this was smaller? What if this took longer? What if this didn't take as long? And so now it's not just one dead image on a page. You've got something that's much more dynamic. So this approach is basically taking advantage of the English word representation and pronouncing it representation. And you change the function and represent it. You change the function and represent it. And multiple representations help you form, understand, interiorize the representation.
But you've created a dilemma for us because you've convinced us we can't trust Google or Microsoft. But
You don't have to trust us. The dilemma is you have to test it. You have to have a reason to believe it. You have to have things that you know to be true that you test it on. And if we don't have any a priori way of guessing what you would test us on, you could figure out where it is and how it works. Oh yeah, you got to do a lot more than that, especially because of Google. Because you come up here and say, oh, I want a simple plot. Oh, I want to study rabbits and wolves.
Wives.
I can't even spell wolves and it doesn't care. You know, you come up and say, my kid's in 3rd grade and I don't want to help him, so I'm going to stick him in front of the computer and let the computer ask him, does he know adding, subtracting, multiplying, and dividing? So one of the things that we have to go and tell you is, yeah, there's a lot of stuff that's out there and we've built a lot of it. And it may or may not be good. We think it's good because it's been tested. We don't think it's good because it comes up first in Google. But Google has an algorithm that looks at what you search for, and if you don't like it, you come back and search again, and then it remembers where you ended up. And if you are the one where it ends up, then you move up the food chain so that Google gets a reputation for giving people what they think they want. Remember the calculation? It does that because it thinks that's what you want. So there's a lot of stuff. And one of the things that we're doing is the other end of the food chain, which is teaching people how to use computers that are 10 million times faster than any Mac or PC in this room. It's called petascale computing. And every year for the last several years, there's been at least one Wofford student who's been picked as a petascale intern. I think that's true. Daniel.
Oh, yeah.
We have a petascale intern.
Yeah.
Dimitri, you were there last summer. So, I mean, there are different things that can be done there. So you're right. The dilemma is, what reason do you have to believe it? And one is because we ask this question of ourselves all the time, and we test it, and every one of our pages has a feedback form that if you have a suggestion for making it better, then you can make it better. And we try to fix them. We also try to make the world come alive. So this is an article, it may be an advertisement first because I haven't been to the website today, which talks about molecular bonds that have been imaged for the first time. And that's not entirely true. It's the bonds that were imaged for the first time in an electron microscope. But several years earlier, we had a model of molecular bonds. You know, we've had other things that could go on. We could actually understand it. So, you know, you could come up here and think about that and then come over and say, what if we had the ability, and I'll just sort of run this to begin with. Has anybody heard of simulated annealing? It's a method for doing optimization. In physics, we use simulated annealing to simulate annealing. So this is something that starts out as a gas and then liquefies and then solidifies, and then if you actually come into these things and figure out what is the electrostatic potential at every point in space, then you can figure out what's the chance that these things are coming in. And all these electrons and electron things are being done, and we're doing hundreds of thousands of calculations a second that you could never do if you were doing this by hand. But the basic idea is very simple. Every square is replaced repeatedly by the average of its neighbors. Now the electrons aren't averaging their neighbors because they are the electrons, right? But everybody else, you know, is sort of coming in here. So if I actually come back and look at the surface and reset that, and I come over here and put some large, oh, that's not what I want to change. Where's the wall values? Okay, so then depending upon where these things are, you know, as things are coming in, then here's the wall charges. I have a different resolution, so I have things set up. So one of the things I need to figure out is I can't use the same number of electrons, but I could come up here and see if I can find it because they have moved. Number of charges, 19. Okay? So what I have is a very repulsive system, and in that very repulsive system, I'm then coming up here and pushing things together, and I don't know if you can sort of see that you've got sort of one atom here surrounded by the other particular atoms that are going through there, and then I can come in here and say, let's show you what it would look like if I actually looked at the bonds. Have you seen something like this before? So then we can ask and answer questions. How strong would the fields have to be to produce what was seen in this article on an IBM journal? You know, we can ask the what if questions. We don't have to, you know, have the same equipment on campus. We can do a reasonable simulation of the things that are sort of going on in that particular case. So, you know, this idea of computational thinking, Hamming, who's a great computer scientist, that said, the purpose of computing is insight, not numbers. And a lesser person said, yeah, but if you can't trust the numbers, you're not going to learn anything. So at least in terms of what we're trying to do, there's a whole set of skills in computational thinking that may not be there if you're using the technology for blogs, or like Dave told me about Piazza. We do that for class discussions and threaded discussions, questions and answers. That's great. But the curriculum, some of which has been developed here by Angela and George Shiflett, true interdisciplinary team skills, so that not everybody has to be a coder, but you need to be able to work with people who are. Understanding the actual technology, like rounding truncation, it matters at some point. Having some ability to do mathematical modeling. What does a constant look like? What does a line look like? What does a quadratic look like? You know, what does a logistic look like? And having some sense that even if you don't know and remember the equation, you know what it looks like, and you can spot it again if you see it. What's this? I don't know, but here comes a whole herd of them. So but the point is that it's pattern recognition and characterization being more important than mere symbol manipulation. And a lot of that stuff can come in, especially when you want to quantify history with sales data of different goods and services between different countries at different eras, or you want to look at, you know, economics issues, or you want to look at other types of things that are done. I mean, it's being done in linguistics, right? I mean, they're doing all these new concordances. If you want to get into the, you know, so what is, from a biblical standpoint, so there may be people on campus, we actually had a computational theologian. What's the number one verb associated with God in the Old and New Testament? Being. Does that surprise you? I am who I am, God is good, God is this, God is that. Being. What's the second most frequent verb? Giving. God gives this, God gives that. Well, how would you know? Well, somebody counted them. Really? Not like this, but at some point somebody might have done that. But now that we can scan the whole thing, it's all digital, we can count, we can sort, we can alphabetize, we can try different versions. I mean, we can ask and answer quantitative questions about linguistical things that are different, try to see what's in there. So as these things are sort of coming up, this is another example of digital pedagogy. This is a quote attributed to Einstein. The actual first appearance of this was in the late 70s by a computer science author who always felt that he would be taken more seriously if he started his sentences with, as Einstein said. And then he would say what he was planning to say. And it kind of got out there. Oh, Einstein said. The point is, there weren't computers when Einstein around that could have possibly satisfied either part of this definition. Okay? So that's one of the things that we try to do is, you go out and you do a search, you get something, well, how do you know? Right? This is one of the things. But, you know, as one of the aspects of digital pedagogy I've seen on different campuses is they want students to become producers of information and not just consumers. And they are producing something. The question is it of any quality and information? The whole Web 0.2 revolution is trying to turn everybody into a producer, and now at least some of us think Web 0.3 is, yeah, but there's got to be an editor somewhere. I mean, even the Wikipedia thing, there's a lot of pages that need expert editing that you're not going to be able to trust it if it's going to be left the way it is. I mean, some people talk about this sort of collapsing under its own weight, you know, sort of as you're coming through here. And you know, you don't know what it's going to be when it actually gets there. We're also up against forces stronger than any of us. This is something that I gave a talk at Notre Dame, found this very interesting. So let me summarize the thing on the digital part of what we're doing, at least in math, science, computer science, and by science, it's anything that's got quantity in it, right? So, by the way, chapter 24 says why that's going to happen. It's in the book. By the way, if you use a different translation, instead of windows, it says gates of heaven. But the idea is there are things that we can do, but if we're going to use technology in the explorations, we have to be willing to take on a much broader role of challenging the students themselves to not just use it blindly. We actually have to go through things in a much deeper way if we're going to insist that they be able to answer the question, how do you know if it's right? What evidence, what reason do you have to believe it, right? And there's things in modeling, and there are modeling tools that are really advancing in sort of a pre-coding world where people can build numerical computational models without actually having gone through several semesters of computer science, because the tool will take an image or a concept map and turn it into a working code. The tool will take a story. You know, if a healthy person is next to a sick person, there's a chance that the healthy person becomes a sick person. If you can write that sentence, you have already written the code with the right software that NSF paid to have developed. And it's online, and we're going to be using it for the first time with undergraduates here by the end of this semester. But there are things that can be done that are really quite challenging, but you can't do it without accepting some responsibility of holding your students to some standard. Right? And that's everything from looking up a number to looking up a model, and it might be something that came from Schroeder, it might not. It might have come from NASA. You know, turned out NASA had a wonderful model that looked at, you know, a simulation of an airfoil, and there was a minus sign that was wrong. You know, and it turned out that was the same minus sign that was wrong in the flight simulator training the first people flying the shuttle. Right? So they did all this training on the flight simulator, and then they put actual humans in the shuttle simulator, not simulator, the one without the engine, so all it could do was glide. They dropped it off the 747, and the guy started doing what he did in the simulator. He says, uh-oh, there's a minus sign. And he had to completely change left and right foot, left and right turns, but he was a good enough pilot he could do that. Right? But even people at the level of that, you know, how do you know if it's right? At some point, you have to fly the thing and see if you've got the minus sign right. Now, the last little soapbox thing is to remind you that data is the new ink. When computers first came out, they used to sell you printers, and the ink was very cheap. And they found out very quickly they could give you the printer and charge you for the ink. And the same thing is happening with a number of digital devices, right? That they're taking things, and more of the websites you go to have video. More and more of the things that you're doing are intended to be necessarily large data versus small data. Like, let's see, if you came over here and you did messages, let me just send a message here. And I'm going to type hi and send it to AT&T. Right? H-I. That's 2 bytes. Now I'm going to turn it sideways, and I'm going to write hi. Right? Then I'm going to send that. That's 16,000. Because I'm sending an image of my writing the word hi. Oh, but isn't that a cool picture? Yeah, but if you're paying for the data. And that's one of the things that I'm not criticizing anyone, but a couple weeks and 4 weeks and 5 weeks ago when we had these network outages, it became bring your own network. The kids in my class that had a data plan got their homework in on time. The kids in my class that were submitting their homework over the campus network did not. And that's a new phenomenon for things going on. So again, the whole thing is who's paying for the data, where's the data, and how much of it is there. Data is, you've got to think in terms of digital pedagogy of where's the data, how much is it, who's paying for it. And if your students end up in a bring your own network situation, that can be hard for a lot of your students. I hope I didn't mess up the digestion of your lunch. Thank you for having me, and let me know how I can help.
Thank you.